Coming up soon.
You're really skimping on attendance today. What are we in, chapter 7?
Yes, we are.
Oh yeah, there's the can there. Okay. Seriously, where is everybody? 3 o'clock.
It's not Wednesday.
Oh, made it in the nick of time.
Colin, anywhere with you guys?
Yeah, I hope it's.
All right.
Look at that. Like, this is signed. What?
How do you pick it up all day long?
Wow.
Fine.
All right, there we go. Keep out the riffraff. All right.
Did you just lock the door?
Yes, I did.
Yes.
So today, we're going to talk about shear flow. So, this is kind of a weird name for the concept, but I'll sort of I'm going to try to explain where it comes from and what it sort of means. So if you have built-up members, so you imagine, you're trying to make some kind of a rigid support for your basement stairs at home. So you take 2 2x4s, like a T. You guys are bending in construction. Right, so 2x4 is good strength this way, but not so much this way. Right? It can wobble. So you make a T joint like this, right? So the place where you're going to experience the greatest shear stress, or where you're going to be most concerned about shear stress, the greatest shear stress occurs right here at the neutral axis, right? We already talked about that. So, had your chance, muffed it.
Thank you. I'm really sad and pathetic as I possibly could out there.
Could have taken one of the chairs, just got up to the window and you're starting taking notes.
All right. So that's where the maximum shear is. But we're typically not really so much concerned about that, right? The point that we're really going to be most concerned about is the shear at the intersection where the two meet, right? That's because that's where there's no rigidity. We have some kind of fastener or something fastening them. They're glued together, they're screwed together, they're nailed together, something. Welded if it's steel, right? But we have some kind of a weak spot at that joint. And so we want to, what's critical for us to know is the force per unit length at the joint. We need to know the force per unit length. So in other words, how much force is there going to be on this thing? So if we have a vertical shear here on this member, then the bottom one's going to want to slide out from the top. Right? From our analysis last time. Remember that. Right, there's going to be a shear and so you can imagine if I try to bend this, the bottom one's going to want to come out while the top one stays in, so we're going to shear that joint. So, do you see what I'm saying?
Which way are you going? Say it one more time.
So, if I have this thing like this, and I try to bend it like that, right? See how that's wanting to slide?
Yeah.
Right? So, you want to prevent that slide, otherwise there's no strength. There's no point in even having a second member. So, the whole idea here is to connect these two so that the bottom one doesn't slide out from the top. Okay? So we want to know how much force we have per unit length. So if we have a 6 foot length of 2x4, we want to know, are my fasteners going to have to hold 600 pounds per unit, per foot. In which case I've got to have 3 fasteners, because each fastener can only hold 200 pounds. Or is it hold, you see what I'm saying? So if a screw can hold 200 pounds, then I gotta know how many screws I gotta put along that joint. So everybody understand the concept that we're after here, the force per unit length. Okay, we wanna know how much shear force there is per unit length along that joint. So we know that the shear force is equal to the shear stress times the area of that intersection, that plane. Right? That's the definition of shear stress, force per unit area times the area. Okay. What's the area of this plane in terms of the values that we had last time? That we talked about last time? Remember? Anyway, let me page up to the canned ham again. What are the dimensions of that interface on which that shear stress is acting going to be? It would be dxt in this picture, but for the whole beam, it's going to be L times T, right? So area equals L times T. L, the length of the beam, T, the width of the interface, right? So this becomes tau times L times T. Force per unit length divides the L out of that, which is tau times T. What's tau? Does anybody remember Monday? It was oh so long ago. What was tau on Monday?
What was like the equation for tau?
Right, the expression for tau.
What's in one Q over IT?
QV over IT. Tau was equal to Q V over IT. Remember, Q was a parameter that was defined by, in this case, it would be the top area. Right, so in this particular example, Q would be the product of the centroid of the top times the area of the top. But then V, I, and T are defined by the whole member. V is the total shear load, internal shear load. I is the moment of inertia of the entire T, and T is the width, the point of that we're trying to figure out. So if I take tau times T, that's Q V over I T times T. The T's cancel out, and I'm left with Q V over I. That is the force per unit length, which we call the shear flow, lowercase q. So the shear flow, we use lowercase q, and that is the shear flow. It still depends on q, so we still have the piece above it. But that's the force per unit length along that axis.
So it ends up not, having any relation to the thickness?
Right, has no relationship to the thickness at that point. Because it's force per unit length, so we're basically normalizing out the area, which is how the thickness got in there in the first place. So it only depends on sort of the macroscopic dimensions here. Okay. Now, it's called shear flow. I wanted to go through, I'm going to take a moment and go through that I-beam picture there and talk about why it's called shear flow. Because last time I took just a purely vertical member. Remember I did a vertical member and we had a certain amount of force on that side and a slightly smaller force acting on this side. Right? Remember that? Neutral axis was down here someplace. And so there was an imbalance in the two forces that had to be made up for with the shear stress or shear force on the bottom surface of that chunk. Everybody remember that, right? Well, now what I've done is I've taken what happens if we have an I-beam? Okay, so we have an I-beam here. And now, instead of having a vertical member, right, well, I mean, it's still vertical, but now I'm going to have to try to draw it in 3 dimensions. Excuse me. The I-beam comes back in this direction. Something like that. That was graceful? I think that's about right. Okay. So now, this was, remember, this was looking at it side on. Okay. So I still have more force if I take this slice of the I-beam. And so now I just take a slice of the I-beam. Okay. There's still going to be more force pushing in here on this side than there is pushing forward from the back side. Right? The total force pushing on the front of the I-beam is going to be more than the force pushing from the back of the I-beam. It's the same thing here. I'm just taking this profile picture and tilting my I-beam so I look at it from the side. So if I take this little element out here, at the end of that I-beam, that's what's shown here in the picture on the right-hand side there, right? Now, the force to compensate for that has to be on this face, not on the bottom face, because there is no bottom face to support that load. See over here, I said, oh, the shear stress must be on the bottom face, because it was just a vertical member. But now, in this case, in the I-beam, the shear must be on the inside face. That's the only place I can apply any extra load, because the surfaces can't bear load. Right? There's nothing on the surface. You know, air can't apply a force to the surface. Right? So that stress now, instead of being on the top and bottom, so if you look here, in the bottom left, before we had the top and this front face. So these were the 2 directions of the shear load. Right? And then the arrow on the bottom would be pushing from left to right. See me? You see the picture? So that was what we had before. Those have to be 0 now because the top and bottom of this end of the I-beam are actually can't support a load. They're exposed to air. So the stress that compensates for that extra force must be on the inside here. Does that make sense? Okay. So that means when I look at this I-beam here, if I want to draw the stress on the front face, instead of being downward, like here we had, we would draw the stress downward on the front. Remember I drew the little box? Instead of it's this way here, it's downward here, and here, and here. Remember that was the stress configuration for that chunk of material? Now because this chunk of material is rotated around, now for this chunk of material, if I look at it from the front, I have this piece going across on the front face, and then, I didn't draw that very well. I have it going across on the front face so that it's going this way on this face. On that little chunk at the end. So you follow my picture. So the point is, the orientation of the shear at any point is along the direction of the narrow member. And so here, when it's a vertical piece, that front face is pointing downward toward the neutral axis. If I look at this, if this is just a beam, I look at it from the front, that top piece, the shear is pushing down here because this and that. This is the tau here, and that's the tau in the front face. You guys getting the 3-dimensionality of what I'm talking about here? Now on this one, it points this direction, but it always points along the narrow section back toward the neutral axis from the top. Similarly, so that's what's shown here in the picture. So the vertical piece is gone. It doesn't exist because those are on because the top and bottom are 0. But these side pieces are present because that's the flange, the orientation of the flange. So, if you kind of bear with me then. So if I look at the whole I-beam from the front face, or from the section to face, the shear at this point is pointing inward. The shear at this point is pointing inward that direction. We do the same analysis at point C as we just did at point B. And it continues to point inward until it gets to the center where it begins to point downward, just like we had before. And the bottom is in tension, so it continues to point downward and then outward toward the sides. So the direction of shear in the beam follows the beam, and it appears to flow through the beam. See what I'm saying? So the direction of shear is always along, along the, and then, the compensating shear for this top piece would be coming out of the board. Right? So if I had this little chunk here, if I have this coming across the front face, then I've got a piece coming out on that interface. And similarly here, if it's going this way, then it would be coming out on this face or going in on that face. Because it's in tension down here and compression up there. Okay. So that's why I just wanted to point out that the direction of the shear is always along the narrow portion of the beam. So when it's in the flange, it points to the center. When it's in the web, it points down, assuming we have the loading configuration I talked about before, which was, and which I'm sort of bending it up.
What is this direction of the shear? What is that? What kind of analysis would we need that for?
So when we combine, so if I were to twist this at the same time, right, if this were not only bent but also torsion, then I'd have to know how to combine, as we'll do next. I have to know how to combine this shear stress with the shear stress from torsion. So if I take this thing and twist it, then I'm adding a shear stress in that direction to this one. So I'm increasing the shear stress here, but I'm actually opposing the shear stress there. So I'm saying, so when I twist this, if I bend this and twist it, this corner is going to be most heavily stressed, and this one less heavily stressed. So I have to know the direction of the shear in order to be able to recombine them later. Okay. So that's what it's after, yeah.
When you do combine them, it's just superposition, right?
Right, yeah. Yeah, again, we'll talk about that. I mean, really, a lot of chapter 8 is just sort of combining everything we've done in the other chapters in, having multiple states of stress and sort of finding out what the total stress is. Okay? So I want to make sure you understood the concept of shear flow and where it came from. I think I might even have, yeah. So here's the diagram showing that, with the arrows coming in. Notice there's 0 stress at the surface, at the end of the flange, because again, there's nothing here to support a stress. So there's no stress on the end. But as it begins to grow in, as it comes in from the end, it linearly increases along the flange. Okay? And the reason for that is because we're just integrating a constant function. All of the top flange is experiencing the same normal stress, the same difference front to back, because it's all the same distance away from the neutral axis. So everything along here is experiencing the same difference. So as I integrate in from the end, I integrate a constant force, and I get a shear diagram that's a slope. Right? But then when I go vertically, now I get a quadratic shape because it's not all constant. The shear is no longer constant. I'm now integrating a slope. I'm integrating this slope as I increase as I come down here, and therefore get a quadratic expression. Okay.
So
Go ahead.
question. So the
maximum shear stress is gonna be in the center of the
The
web?
maximum shear stress is always at the neutral axis.
Okay.
Okay, that's where the maximum shear stress occurs. But the maximum shear stress in the flange is where the flange meets the web, right here in the center. The maximum shear stress in the web is at the neutral axis.
Is that, and is the shear stress of the flange, is that the flange breaking away from the web, or is that the flange breaking in half?
I'm trying to figure out what you.
Like,
So it
say,
would be-
say you
it would-
stress
it would be,
into
it would be the
deformity.
flange breaking in half if you're, I mean, it's not breaking in half, it's shearing, but.
Right,
So yeah, so you're doing this in the flange, right?
So, yeah, there's like two pieces in one.
Right,
Okay.
okay. So what's this stress right here, right there, is the stress the shear stress that would break the flange away from the web. So the
Okay.
web shear stress, over here on the right, that quadratic thing, represents the stress moving the flange away from the web. The one across the top here is the flange moving relative to itself.
Okay.
So typically, this is the one we're going to be concerned about in the structure, because it actually wouldn't be that one, it'd be the one slightly below it here, right? But it would be this point that we'd be concerned about, right where the flange meets the web, because that's when you're going to have nails or glue or screws or whatever holding the thing together, or weld. Okay. I think that's all I had about shear flow. Anybody have any questions? Other questions? Okay. So let's look at some problems. Okay, we have three identical boards bolted together to form the built-up beam shown. We see it? Each bolt has a shear strength of 1.5 kips, 1,500 pounds, and the bolts are spaced at a distance of 6 inches. If the wood has an allowable shear stress of 450 psi, determine the maximum allowable internal shear that can act on the beam.
I think we better start with the free body diagram.
Free body diagram of what?
I wanna say the face.
Cross-sectional face.
Yeah.
Well, then why don't you say the cross-sectional face?
The cross-sectional face.
All right, very good. And there's our cross-sectional face. What now?
So, if we have the shear stress and we're looking for V, do we just use TAC equals QV over IT? Sorry, we need to put the dimensions on this.
Okay. Jumping right to the end, you know. Okay, so we have each of these is 1 inch. And I think this is 2 inches, 2 inches, and 2 inches. So these are 1x4s, essentially. And then spacing, the 6-inch spacing is into the board. We don't, yeah, no, that's not on our diagram. Okay, now what? What kind of things we're gonna need to know? If we're talking about shear stress, what kind of properties are we gonna need?
I think we can, one thing that we could do is we need some forces in for the base. So, you know, there's that force V pushing down on that member in the middle. Then there's gonna have to be equal and opposite, for two forces that are half of V on either side.
So V is, I think, the total shear that's acting on the composite beam.
It's not a force.
So we're grabbing hold of this thing and we're pulling it down with V. Okay, the whole thing is experiencing a downward V, not just the center member anymore.
Oh, okay,
See what I'm saying?
Mm-hmm.
It's a composite beam, so the shear forces, the shear load is being applied to the whole beam.
So we'll be,
So we're not really looking at characteristics within the beam. And treating it as one beam, and we're going to find out what the shear forces or shear stresses are. So we know we're going to have to find some shear stress, right? So at the very least, we know we're probably going to use somewhere these two expressions. Right? Because it's talking about shear flow. Well, actually, no, it doesn't talk about it. It talks about the bolt strength. That bolt strength is analyzed through shear flow. And we're talking about a maximum allowed shear stress. So we know we're going to have those two expressions. Do we have Q, V, I, and T? We can get them. So we probably ought to get whatever we need, right? So which ones we're going to get? What thing you want to get first? I would disagree. So if I'm going to get anything first, I'm going to get I, because Q is specific to what location I'm looking at, right? Q depends, am I looking at the point of the wood up here, the point of the wood here, the point where the bolt goes through. Q varies based on what position I choose. I is a universal parameter for the whole cross section. Right? So I probably want to find I. How would I want to find I? How do I find I?
Well,
let's sum the inertias of the three different pieces of wood.
With respect to what?
The y-axis.
Yeah, but with respect to what location? Where are we going to put the origin?
what's the neutral axis?
Where's the neutral axis?
Straight up the middle, or it'd be 1.5 from the either side.
No, because we're bending in this direction. So the neutral axis is the horizontal axis, bending vertically. So where's the horizontal neutral axis? What's it go through? What do we call the geometric center?
Centroid.
The centroid. So we're going to have to find the centroid too. Right? We got to find the centroid, so we can find the neutral axis, so we can find the moment of inertia about that axis. Okay, so which one are we going to find first?
Centroid.
Centroid. How are we going to find centroid? What's the definition of centroid?
The integral of
Area.
it's going to be y dA over volume.
Yeah, except that these are nice uniform shapes.
So we look it up.
So we look them up, right? It's the sum
We won't usually have to
Oh,
calculate
total area.
centroids, will we? Like actually calculate them with the integral? I mean, you normally.
No, but you'll have to calculate them with the sum.
Right.
I mean, you'll have to, because you'll have compound beams that are, maybe are stacked up beams or whatever. Okay.
So you have two from, which way are we summing them? Are we summing them in the y-axis or in the x-axis?
What direction are we bending?
We're bending vertically, so
Right,
either,
so all we care about is the vertical. That's why we're Y. We're not bending it horizontally. If we're bending it horizontally, we'd have a different question. Okay.
so you have two at 2 from the bottom, and you have 1 at 4 just from the bottom.
So from the bottom, we have these two
Right.
and that one.
Yes.
All right, so we have 4 times, what's the area of that member? The top number? 4. Right, the Y? Area of this top member?
4? 2 inches times, plus 2 inches times 1.
Oh, 4, you're right. Woo! All right, sorry. 4 plus 2 times 4 plus 2 times 4, all divided by 12. So that's nobody knows. Mental math, guys.
40 divided by 12.
32 divided by 12. 8/3. Okay, so the center's 8/3. So it's gonna be 2 and then 1/3 of the way up. That's my center, that's my centroid. 1/3 of the way up in the sort of 1/3 of the center section up. Right? Okay, so now I know where my centroid is. How do I find my moment of inertia?
We'll now add up all the moments of inertia of each of these beams with respect to that axis.
Okay, which are? What's the moment of inertia of the top beam with respect to that axis?
It's gonna be 1/12 base, which is an inch, times 4 cubed, I think. This is 4 cubed. And it's gonna be plus something r squared. Is it just r squared? Which is the distance from the centroid to the.
It's not r squared. Let's see if they did it that way, if they subtract it.
Would you subtract from, the small area that's on the other side of?
It's,
The
the expression is 1/12 BH cubed for a rectangle. And then the parallel axis theorem is A r squared, D squared, I think is what they use. I think it's AD squared, AD squared.
And then d is the distance from its centroid to the centroid where we find the moment of
Right.
Is A the whole area of the object that we're calculating the moment of inertia from? That makes sense.
In this area?
Yeah, is it that same area, that 4? Is it the full area?
No, the area here would be for the each individual, you're doing each individual piece.
Yeah, that's what I'm talking about, the 4. Is it the 4 or is it just the area like above the?
No, it's the 4, it's the area of the whole piece.
Okay.
Okay. Want me to spritz some water on you? Yeah. All right. So the area here is going to be plus 1 times 4 times, and then D, what's D? You can offer me to smack.
I thought you wanted to kiss at first, I was like, what?
1 times 4, what's D? What's D?
D is gonna be.
We're doing the top beam first.
4 minus 8/3.
Right. Okay, that's moment of inertia of the first piece. Now what?
Plus
What is this?
1 12 times your base times your height cubed plus 4 times r, which is going to be 8/3 minus 2. We can go ahead and throw a 2 out in front of that.
There you go. Everybody follow that?
Boom.
And according to them, that's 26.6 repeating inches to the 4th. Or 80/3. Okay, so now we have now I have C and I. Now what? Each bolt has a shear strength of 1.5 kips, and the bolts are spaced a distance of 6 inches. Wood has an allowable shear stress of 450 psi. Determine the maximum allowable internal shear that can act on the beam.
So now we want to find Q, right? Well, we need to decide where
Where we think the maximum shear stress is going to be?
which will be at the neutral axis.
Right, maximum shear stress occurs at the neutral axis.
So we need to find Q with respect to the neutral axis.
Right. So how do we find Q with respect to the neutral axis?
So Q is the centroid of the area above the neutral axis times the area above the neutral axis. The centroid above the neutral axis.
So I recommend then at this point a new
Free body.
a new free body. Okay. So now we're going to draw a free body diagram of just the top half. Right, so this dimension here is well,
Dr. Secondary,
yeah.
how do we decide, so this one's on top, but how do we know if it was on the bottom?
It's the same. Remember the shear flow thing I showed you? For
No, it
instance?
doesn't matter, we could go on the top or on the bottom.
Right, so the shear stress depends only on Q, right? So we're gonna get the maximum Q. Maximum Q is going to occur at the very top or at the very bottom. Right? So, and so it doesn't matter, we're gonna calculate Q essentially for this top, for the top piece, but the Q of the bottom piece has gotta be equal opposite to it, more for the height of the down, so. Because the shear here in one direction is equal to minus shear in the other direction, calculated from the bottom up. Okay, so we got this top piece, 10/3 there, and this is 8/3, and that is 12/3, so this is 4/3. Right. Okay, so now what's Q? Oh, how am I gonna find Q? What do I have to do to find Q? What am I have to do first?
Find the centroid.
I gotta find the centroid of the top piece, right? So the centroid of the top piece, or actually, I'm probably gonna find y bar times A. Or y bar prime times A prime. Because if I find the centroid and multiply it by A prime, I'm just doing the sum of this piece. See what I'm saying? So I just have to do the sum, I don't have to divide by area, then multiply area again. Okay. So, that's going to equal the sum of the y tilde primes, A prime I for I, So it's gonna equal, all right, let's start with the big one again. What's y tilde prime gonna be of the big one? What's y tilde prime gonna be for this?
It's gonna be half of 6 minus 8/3. Oh, I already had it, 2/3.
So what's it gonna be?
10/6.
Yes, or 5/3?
5/3.
5/3 times what's AI?
That's math, sorry.
10/3 times 1, so.
Right, so 10/3. What about for the sides?
4/6.
2 times, first of all,
2/3.
2/3 times
4/3.
4/3. We follow that? Does that make sense? How we got there? Okay. That is, oh shoot. Q max. Here we are, 2/3. 2/3. What is that? Times 3. What do you get times 3? No. 5/3. Oh, they did it, I think they did it differently. E and D. I can't figure out what their numbers are, so I just wanna make sure I'm getting writing the right numbers down. They have these weird. They say that's 7/3. Or 7 1/3. So 22/3. Let's see if that works out. That's 25/9 plus 2 times 8 is 16/9, right? So 25 and 16 is 41/9. That doesn't seem to work out, no. We have 4/3. I don't know. I'm not sure what they're doing there. I'm not sure where the numbers are coming from. Oh, no, wait. Never mind. They're doing something different. Yeah. So I don't know what their numbers don't make any sense to me. Okay, sorry. So that gives me the total for that whole chunk. But what would that be? What is it?
Because 5 times 10 is 50, and then.
Oh, 50, I did 25, I did 5 times, I don't know how I got, okay,
So
so,
66 over 90.
okay, which is 22 over 30, okay. I'm glad you're paying attention, Ben.
Make it
I was
extra.
getting myself all confused. What's that?
Make it extra credit.
No. But thank you for playing. Lovely parting gift. Okay, so that's our, you know, they broke it up differently. I think they broke it up into a piece this way and a piece that way. It's kind of weird. Whatever, we got the 22/3, okay? So what's that cube? So that's what, that's cube, right? So that's my cube,
Right.
okay? Now what? Q max. So that's my Q max. Which Q am I working with here? Q max. Where do I care about Q max? What am I trying to find? Is it this Q or this Q that I'm looking for Q max?
The bottom.
The bottom one, right? So looking for the maximum shear stress. This Q corresponds specifically to the location of the bolts, not the maximum Q. See what I'm saying? With shear flow, we want to know about how much the bolts have to withstand. The bolts are not located at this height. Right? The bolts are located ever ever so slightly above that, that's where the bolts go through. Or that is 1 inch.
It would have not been smart to put the bolts right at the neutral axis, would it? That's the max shear, so that would reduce
That would-
the area.
Presumably. Okay. But nonetheless, okay, bolts are there. There are other reasons that the bolts would go where they are. In fact, it doesn't actually specify where, does it? I mean, it draws them in the center, but it doesn't actually specify that they're in the center. Okay, okay, so that's my Q max. So now what do I find? What do I do?
The thickness at our neutral axis.
Is
3.
okay, we got that. So we know T equals 3,
And so our equation equals V.
right? So then we have V is equal to I T tau over Q max. Is that what you're saying?
Yeah.
Okay, we're just rearranging that expression. And let's see here, that means we have 80 thirds times 3, that's 80, times tau, which is 450, divided by Q max, which is 22 thirds. And that gives me 2,571 pounds. Oh, no, it doesn't. Oh, no, I take that back. Now I understand why they were doing what they were doing. Okay. 4,909 pounds. Somebody else get 4,000? Nobody did.
I'll check.
Okay. 4,909 pounds. Okay.
You got 4,900?
4,900.
636 pounds.
Really?
I got 49 on
Okay.
I might have done something wrong. I'm not really having a good math day.
Really? Well, you are using a phone for a calculator. Okay. So,
Yeah, it's really dumb.
all right, so 4,909. Okay? Is that our answer? Is that our answer, yes or no?
Yeah.
So that is our answer if we assume that it fails because of the wood failing, not because of the bolts failing. We have to go back and analyze it again from the standpoint of the bolts to find out if they would fail at a different stress.
there. Where Q comes in? Like Q equals, that's big Q equals V over.
What's that? A little q?
Yeah.
We use the shear flow.
And apparently, let's see, I'm trying to find out what their, yeah, they didn't, they solved for QB. I'm trying to figure out where the bolts are. 'Cause they, they don't tell you on the picture where the bolts are. I'm having a tough time figuring out from their example, from their solution, where the bolts officially are. You know what I'm saying?
Yeah. My guess would be 4/3 at 3 inches from the bottom, but that's just a guess. So if,
Yeah, I don't know, I can't tell from the picture, I mean, they've got some kind of, go ahead.
if we knew the distance at where the bolts were at, and we know that the bolts can take a shear strength of 1.5 kips, and we know that our force at the center is 4909.
That's the shear force that will cause the wood to fail,
Yeah.
if it fails at the neutral axis. The other thing is, we didn't go back and analyze it, but, it could fail there. Right? Because the total shear force increases as we come down, but the shear force from here on down is distributed over a larger area. So the shear stress might actually be higher right there at that location. You see what I'm saying? So anytime there's a dramatic change in thickness like this, so when we did the I-beam, we're gonna be out of time, I'm not gonna be able to get any further. When we did the I-beam, I said we knew what maximum shear stress would occur on the neutral axis, because that's where T is small, right, and Q is big. So we're gonna get the maximum shear. But in this case, we're just kind of the opposite. T is the biggest at the neutral axis and smaller up above. So you actually need to find Q at that location as well.
And bolts.
What's that?
And at the bolts.
And at the bolts.
Is the 1.5, the shear strength of 1.5, is that saying that the bolts can take a shear strength of 1.5 before they fail? Is that what
It
that's
says
saying?
it can withstand 1,500 pounds of shear load
Okay.
before failing.
Okay.
So you take the thing and hold the bolt right here, and put another thing right here, and pull down 1,500 pounds. And then shear off. Okay. But yeah, I'll have to figure out why they didn't, it's not clear where the position of the bolts is.
To be determined.
Yeah.
Time to go run in the rain.